Welcome back. The next speaker is Randall.
Thank you so much for having me. I had to change my name tag earlier just because I'm no longer actually at Netflix. So I was at Netflix for about 4 years. And then about 8 months ago, I left Netflix and joined a stealth mode startup to do some continuing R&D based on this work, as well as trying to turn it into a more scalable product and service so that not only Netflix can benefit from estimating incrementality and sort of bringing these things together, but also hopefully the rest of the world will be able to do it, because it's kind of hard to build these things. At least I found it was hard to build them, and I want to make it easier for everybody else to benefit from them as well. So first off, just by a show of hands, who here knows what the word incrementality means or has heard it before? Okay, all right, so we've got like a few people. Who here really loves econometrics? And how about machine learning? Who's taken a stab at machine learning off and on? Okay, so this talk is going to be kind of a blend of these three main ideas put together in a practical application. As we start thinking about sort of information platforms and sort of algorithmic game theory, those types of concepts, well, we're primarily going to be applying this in a setting where you're trying to estimate a best response function. So you're basically trying to write down an algorithm that is going to give you the way to make a decision for your algorithm. So let's get into the details here. So give you guys a little bit of background. Hopefully this thing's working. All right, great. All right, so it's worth noting that it takes a lot of people to do this type of research at a company. You need to have people like management to give you the freedom and finances to make it happen. You need people to actually then go and execute the actual work as well. So like this work is not just me. It represents a whole bunch of people all working together, and I'm really grateful for those partnerships. So first off, why does incrementality matter? I think it's helpful to even understand what incrementality is and why it might matter, especially in the world of advertising, but also in many other applications as well. So for example, when I first joined Yahoo 10 years ago, 11, I guess it's been a while now, I kept seeing plots that looked like this, where we would, before an ad was exposed, people would be engaging in an activity at some baseline rate, and then there'd be a giant spike on the day of ad exposure. So, it looks like the ads are having a huge effect. Everybody in the marketing department's loving this. Across, Yahoo loves it because they're selling a lot of advertising. And then you start thinking about it. Well, ad exposure is happening on that day. Maybe we should just run an experiment just to make sure that things are what we think they are. Well, it turns out that when you run an experiment, you get a control group that looks like that. So there's a gigantic spike that happens on the same day as of ad exposure, even when you showed an ad that was completely irrelevant to the outcome. So what's going on here? Well, we called this activity bias. This is essentially that there's a contemporaneous correlation that when you go online today and you start browsing, you're going to see some ads. And what else are you going to do when you go online today? You're going to buy some stuff. Why weren't you online yesterday? Maybe you were on vacation. When you were on vacation, you weren't buying stuff. You were doing other things. You weren't browsing the web. And so inadvertently, these types of plots end up creating spurious correlations. So in econometrics, we call this spurious regression. This is just trying to correlate collinear things that both move over time, contemporaneous correlations. And it's just another form of omitted variable bias or endogeneity. So obviously, this is a problem. So in the world of ad effectiveness around this time in 2008, this came out in the Harvard Business Review, essentially saying that it's really easy to measure the effect of ads because you just need to compare online purchases by those who have seen the ad and those who have not seen the ad. And some other economists who worked at eBay for a little while, they thought that quote was crazy as well. So what they found is that when you set up these ads for eBay, you have links here that you're paying to get clicks on, and down here you have links that you're not paying to get clicks on. So you don't have to pay for those. And similarly, you'd have like Macy's would advertise on the keyword Macy's. So when you type in the word Macy's, where do you think people are trying to go? Macy's. The types of people who don't type in the keyword Macy's, where do you think they're trying to go? Not Macy's. So it shouldn't be surprising that the people who type in the keyword Macy's and see the ad are going to convert at a different rate. So regardless of the presence or absence of that ad. So this is the foundation of endogeneity, that the actual treatment itself is correlated with the error, that these people are just different and you haven't controlled for that. So when you run an A/B test, here's the man himself. I'm actually giving a talk on your research instead of mine. No, but this work was really great, and what Steve and others were able to show is that when you turned off the advertising, that you see a kind of a direct substitution between those organic clicks and the sponsored clicks. And they then ran another test on Google to see if the effect also held, and sure enough, it did. So what you worry about is when these substitution effects happen, is are you actually losing something as a result? And this is a logarithmic scale, so it actually turns out that roughly there's approximately perfect substitution in both of these cases. So people were trying to get to Macy's, they got to Macy's. People trying to get to eBay, they got to eBay. When you start looking at some of the sort of the classical correlational metrics that marketers are using in order to determine the effectiveness of a campaign, there's a couple measurements here, and we have one measurement which is this blue line, which shows a clear drop. So this ends up being the post-click, or these are what are called the attributed sales. So these are like post-view or post-click type conversions, and as a result, when you turn off advertising, what happens? You have fewer opportunities to correlate sales to marketing. But what you look when you compare a test and control group, at the moment when they turned off all the ads, you don't really see any market decrease in the actual purchase behavior among the customers. And over here, there's another analysis that shows that there's essentially no effect on sales that when you change the marketing. All right, so what they were able to show, first off, they didn't call this paper how eBay was throwing away lots and lots of money by advertising ineffectively. What they instead titled the paper is Consumer Heterogeneity and Paid Search Effectiveness. And essentially what they were able to find is that, yes, there was a lot of money being wasted because the estimation strategy for figuring out how effective the advertising was imperfect. But what they were able to show is that there actually were some pockets of incrementality or causal effect of advertising happening among the subpopulations. So it gave an opportunity to set up arbitrage. So they were able to then change the direction that they were spending from blanketing a lot of people that didn't need that advertising to moving it into more efficient opportunities. And so that's really sort of what we hope to do with this incrementality bidding work. So essentially, the ideal experiment when you set up a test and control group is to be able to track the people who are going to see the Netflix ad, who actually see the Netflix ad, and you want to be able to compare them to the people who would have seen the Netflix ad. And in these auction environments where you're submitting a bid into an auction to win an advertisement, you don't necessarily get control over all the users in the control group unless you actually choose to purchase this ad, but that costs a lot of money. So there's a lot of reasons why you want to avoid that, avoid having to spend the money. And so in another paper, we came up with this idea called ghost ads, where you're able to sort of simulate the auction and learn whether an experiment would have won. And so if you want to learn about that, I think it's a great paper. But essentially what we're trying to do is estimate the causal effect of an ad with incrementality. So we have, in a control group, you're going to see other advertisers' ads. You're still going to visit the web pages. You're going to browse. And then in the treatment group, instead of seeing the other advertiser's ad, you're going to see perhaps this sporting good retailer's ad. And that will cause sales to go up by $100,000. So what we can infer from this, just like we would in any sort of standard experiment, is that we have an increase in sales. And because we had random assignment, we've now solved this endogeneity problem, or this bias problem that was plaguing us at the beginning, in that we now have those comparable groups. So a nice thing to note here is that it helps us estimate what the actual true effect was and translate it into business metrics such as how much revenue we're getting per 1,000 impressions, which is then what the marketers are going to use to submit bids into these auctions. But we don't just want to know whether the ads were ineffective, as in Steve's case. We don't just want to know, is it after the fact, we spent all this money, was it worth it? That's not as helpful as knowing, well, we've spent this money, where was it more worth it versus where was it less? So perhaps we have this group of outdoor enthusiasts. They account for 80% of the increase, and then 20% of the increase is coming from the not outdoor enthusiasts for the sporting goods retailer. And what this allows us to do then is to take the number of impressions that were shown here and translate these into actual willingness to pay, or a maximum value. So in essence, we should never be willing to bid more than $6 per 1,000 impressions if this is the magnitude of incrementality that we're getting. So some basic arithmetic here. But what we want to do is take this idea of outdoor enthusiasts and not outdoor enthusiasts and turn it into basically turn it into a classical machine learning algorithm where today you can go and buy media based off of impressions. So you pay a certain amount per impression, or you pay per click, or you pay per attributed conversion, sort of a conversion that happens after an impression. So as we've seen, some of those metrics are potentially subject to some of these other critiques, where you can end up spending $50 million and be getting a minus, let's say, 80% ROI on that, and not know it, just because you're maximizing, in some sense, maximizing the wrong objective. So what we want to do is figure out how to maximize the yield here against the spend that we were going to do. So that's really what we need to do, but we need to be able to estimate incrementality with a more scalable model that fits within the standard frameworks. Like this type of model is an A/B test, like a user level A/B test, but the reality of advertising is that you don't get to show a person one ad, and usually you don't get to control the opportunities because they're the ones that are controlling the opportunities. They're visiting, they're browsing, they're engaging in ways that you can't like handcuff somebody to a computer and force them to visit a particular web page in order to see that one ad, and then force them to look at it as well. Like all of these types of differences make it really hard to actually differentiate between the people who are going to see the ad versus those who would have seen the ad, and so we need to set it up in a framework that's going to allow us to estimate it not just for outdoor enthusiasts, the type of people, but also maybe for the type of treatment. So perhaps we want to estimate different ad sizes. We want to estimate different characteristics of the ad. Just like if you were trying to treat someone with medication, you'd want to control maybe the dose intensity, and you want to understand how the response is going to vary, or how the health response might vary with that. All right. So how are we going to do that? Well, it helps to understand sort of the basics of causal inference. So who here has heard of directed acyclic graphs, DAGs? Okay, all right, great. Well, enough people that maybe I'll just breeze through this real quick. So in essence, what we're going to do is we're going to run an experiment here that is going to vary the amount of ad exposure. So we're going to set up an A/B test, but not a user level A/B test. We're going to set up in some sense, a treatment level A/B test that allows us to vary this in a way that's uncorrelated with all of these other confounders that are correlated with purchases. So like this is, did you type in Macy's? And what we're going to do is be able to then randomize whether you see that ad or not. Maybe how high we bid, and as a result we'll be able, or maybe what subpopulation, maybe even what creative we put in it. So we'll be able to do all that, and then we'll see how that influences purchases. So in the world of advertising, there's also some of the worst forms of endogeneity that crop up. One of them is known as negative targeting. So for Netflix, we might like to show ads to people in order to get them to sign up for the service, but as soon as you've signed up, we want to stop showing you ads because we maybe don't want to bother you, or maybe it just costs money, and if we've achieved the goal of getting someone to sign up, then we don't need to spend that money anymore, or maybe half of the population is already signed up. So one of the challenges here is that if people if people have signed up, and then that influences whether or not you see an ad, what you'll find is that we start showing ads to all the people who haven't signed up. And depending on how you analyze this data, you have to be careful because you can sort of get your data crossed, in that the people who are signing up aren't seeing ads. So we show fewer ads to the people who have not signed up, and this actually induces a negative correlation between ad exposure and signing up. So you've got to be careful with these things. All right, so in the end, we're going to set up, we have a sort of a simple heterogeneous treatment effects model. So we're going to have an outcome Y for a user I, and we're going to have a treatment X, or treatment intensity X, with user I, and we're going to model the baseline, which is your likelihood of purchasing or signing up, and then we'll have an error term, sort of a standard econometric model. So within, essentially what we're trying to estimate is delta Y, which is the incremental effect or the causal effect of showing an ad by computing the difference in expectation. And it turns out that that's just this coefficient. If we want heterogeneous treatment effects, we just need to interact treatment with other characteristics, and then we need to make sure we have a baseline that's also sort of rich and heterogeneous. Okay. Any questions at this point? All right. So as I said, these are going to be things like ad size, maybe the country that the person's from, et cetera.
So when you estimate the heterogeneous treatment effects, do you know the subpopulation beforehand, or you infer it from the data?
Yeah, so almost always when you have a piece of information so when you have a bid request that comes in, or an opportunity to show an ad, or to purchase an ad, there will be a whole bunch of information that's embedded in there. So it will have all the information about the ad size, the website it's from. Usually there'll be like a cookie identifier of some sort. And then to the extent that there's other information, for example, to know whether or not you want to buy the ad or not. Maybe for Netflix, it was you have to be able to then link that user identifier to know that that person's already a member. So there's some offline data processes that bring that enrich or augment this bid request with additional information.
So, but the partition is done beforehand, right? So in the Netflix example, it would be subscribers versus non-subscribers.
Sure. Yes. Yep. Yeah. So for the most part, you have a database that allows you to immediately look up before you take an action. So yes, there is some sort of partitioning that's done beforehand. Okay. So this type of model is something like the models that I showed right at the beginning that are potentially fraught with bias and can lead you to make those spurious correlations that people who see an ad on the day that they see an ad are going to have that they're more likely to see an ad, but they're also more likely to convert, but in a spurious way. So in order to avoid this, we're going to set up a framework using instrumental variables. So who here has heard of two-stage least squares or instrumental variables? Wow, that's a lot. Okay, so the basic principles of this model is that we're going to set up the randomization information. So when we've actually injected randomization, we're going to put that information into our variable z, and it'll allow us to create a form of least squares estimation that allows us to then retrieve a causal effect under a bunch of assumptions. And so the difference between classical sort of econometric standard using observational data with instrumental variables is that usually with an instrumental variable, you have to believe something. So there's a bunch of assumptions, and you have to satisfy those assumptions. And then when you go to an applied econometrics seminar, there's going to be at least 30 minutes out of the 75 minutes is almost always going to be dedicated to people hassling you about whether they believe your instrument or not, whether they think you have a quasi-randomization that is worth looking at. And now, sort of, let's say 10 or 15 years from when I was sort of going through a lot of this in grad school, now they've gotten even more sophisticated, and now it's about whether that population where that randomization was happening is in fact representative of the more broader population. So in other words, you've estimated what's known as a local average treatment effect or something to that tune, and then we now understand that it's like a weighted average of a bunch of people that happen to have some little bit of randomization in that population. So the beautiful thing about being in industry and working on an application is that I can do two things. I can shut down that 30 minutes and I can instead use it, or not use it like today. I can instead just say, look, we built randomization, so I've satisfied the first assumption. And then the second assumption is I just need to make sure that when I randomize something, it actually changes something. And I can just sort of show you that. So in this case,
That's unique to industry. I didn't
well, it's not just unique to industry, but we can do it at a scale for this type of problem that we can solve it. So, I don't know, what other applications are you? You do, but in a lot of the observational sort of whenever you're trying to do a causal inference within observational data, in many cases you don't have a form of engineered randomization. So if you're doing field experiments, yeah, you certainly have that. So like especially in the development literature, there's plenty of that, and over the last decade, there's been more and more field experiments. So for sure, yeah.
Would we worry that your randomization affects different populations differently because the other bidders are bidding differently on those populations?
Yes. So then that is a great question. So the question is, when you introduce different forms of randomization, it's going to change which subpopulations maybe you're able to treat. So in this case, we're going to focus on just estimating the treatment effect that is internally valid. So the people that we do win with the forms of randomization that we do win, and then there's this question of generalizability that when you've estimated those treatment effects, if now you go and change the algorithm, how will that change the subpopulations that you're able to show ads to? Or maybe there's an even more abstract question, which is, what is the treatment effect, what is the average treatment effect on all the people that you weren't able to treat? In general, for industry applications, we're less interested in that one, just because if we can't treat them, we can't treat them. Or if you can't treat them economically, then then there's no point in treating them. But there's plenty of other applications where those are interesting concepts, or more interesting. Yeah. Okay. All right. So if we want to do heterogeneous treatment effects in an instrumental variable framework, we can do that as well. If we've engineered a randomization, then we can just create interactions with our randomization. And if it's an event level randomization, it turns out it's independent of everything. You can interact it with everything. And this allows you to create models that perhaps have like 10,000 endogenous right-hand side variables or components of the treatment. And then you can construct the corresponding 10,000 instrumental variables. So we sort of push into a realm that where we have enough randomization and we have enough variables. Maybe we even want to push this further into like million feature regressions. Those are the types of things that you can then do using some of the machine learning tools. All right. So this is going to be the workhorse. This is in some sense the core concept that we're going to work with. But we need to take this out of a world where we don't have time. So there's a handful of differences in industry that we really have to address that haven't typically been addressed in the academic literature for experimentation, at least within the ad effectiveness literature. So, all right. So what are a couple of challenges that we have to face? Well, in industry, in sort of these real-time bidding auctions where we're showing display ads or banner ads to people, you're dealing with over 10 billion auctions per day. So there's just like a huge amount of data coming in. You're looking at estimating models that maybe have 1 billion users or approximate the effect on 1 billion users or billion identifiers. You have some of these challenges of like inexpensive ad impressions means that there's probably not a large signal. If there was a large signal, they'd be worth more. People don't pay a lot of attention to them. Usually you have sparse conversions, so there's not a lot of outcome data coming. And another challenge is that you have a continuous stream of data. So you're constantly having to make decisions while more data is coming in and perhaps even adapt to the marketplace conditions. You have things like high dimensionality because the characteristics of the ads are rich. And then you have this problem of correlation causation, which is what we're going to use the randomization for. And then there's some of these other challenges of trying to get people to want to run experiments. Period. So like when I think about why working in ad tech is interesting, it's not because I love showing people ads. Who here loves to see ads? I mean, like, yeah, all right, we got Dean. Dean loves looking at ads. I am not, I got into ad tech because I found that it was a really interesting, rich environment that had this type of scale and these types of challenges to take on. And I feel like if we can solve some of these rich heterogeneous treatment effect problems in ad tech at the scale that they are, then it should be relatively easy to sort of take some of those things that we've learned and apply them to a broad set of other applications. And that's kind of what we found at Netflix. All right, so I'm going to focus on these sort of 3 problems. And how am I doing on time? Do I still have like 15 minutes? Okay. So we've got downsampling is one way to solve this, some of the data volume issues, but you want to do it in an informationally efficient way. We're going to use some continuous time modeling to address the fact that we don't have to worry about feedback or endogeneity on human decision timescales. So typically, if you have a bureaucrat that is creating a policy, then usually there's like a clear event. You can run event studies where you have like a change in the law before and after. In the case of real-time bidding, you have potentially these types of feedback where as soon as you have signed up for Netflix, within milliseconds, we can suppress ads. And so you have this type of feedback that can happen on that time scale. And it turns out if you're bucketing by day all of your data, then you're going to miss out on, you're going to create this opportunity for contemporaneous correlations that will introduce bias. So we want to have a continuous time model to do that. And finally, if time permits, I'll just briefly mention some of the ideas about Hausman causal correction. Yes?
Question on the ghost ads.
Sure.
How do you implement a ghost ad as a bidder?
Yeah. So I'll have one picture that I'll show for that. Okay. All right. So in continuous time, first off, we need to understand maybe what the shape of an ad effect looks like in continuous time. So here's a Super Bowl commercials. The green bar that you can't really see is when the ad happened, and then the spikes kind of look like this, where there's a big spike in sort of people visiting a website or issuing queries for that brand in the time following the ad. Similarly, in display advertising, this is another one of those spurious correlations where this is the histogram of searches for Macy's, say, following an ad exposure, and within the first 10 minutes, you have a whole bunch of people searching for Macy's. Problem is you also have a whole bunch of people searching for Craigslist right after seeing an ad for Macy's. So again, we have this sort of spurious correlation problem where what ends up happening is that people are just actively doing stuff. Like when you see an ad, that means you're about to do something else. So you're about to type in a search. That's just what happens in life. So it turns out, though, that when you set up an experiment, you can also see that the ad effects themselves tend to spike. So the green bar represents the amount of ad effect over and above the blue bars, which show the baseline. So you're able to see that the ad effects, in fact, sort of do spike in this way. So we want to model ad effects that spike in this way. So perhaps we're going to set up we're going to use a kernel, in this case an exponential kernel, to model this effect. And we can, if you say I don't like that shape, well then we'll just add another shape to it, and we'll do a mixture of kernels so that maybe it looks more like an ad effect that you think ads do will look more like. And the nice thing about this is it's parameterized in a way that allows us to actually estimate those mixing coefficients, and then you'll be able to just estimate what that shape looks like. So this is kind of like semi-parametric, depending on how rigorous you want to get about terminology. So then maybe there's not just one ad, but there's another ad. We then stack those on top. If we want to, maybe there's a second ad, and we're just going to say that they're additively separable at this point. Then maybe we add another ad. We also maybe change the size and the shapes, and we can actually, as we start adding more and more features to our model, the effects don't just vary by user over time or by the impression, but maybe also by impression characteristics. So maybe different ad sizes are, there's ad size changes, how big the curves are, or maybe even changes the shape and the dynamics. And so what we want to do is be able to estimate a model that has all of these types that can recover these dynamic treatment effect curves. And why do we want to do that? Well, the main reason why we went down this avenue is that it turns out that that a lot of the approaches in the past that analyze a user-level experiment over, say, 4 weeks ends up integrating all of the conversions over those entire 4 weeks. But if the ad effects only last 1 day, essentially in terms of the lion's share of the effect, then you're increasing your noise potentially by a factor of 28 over what you otherwise could do. And so this is a way to buy a substantial amount of power by restricting the window and modeling those response curves. Yes?
Are you saying these are 3 ads, different types, but they are dynamic, right? So could there be,
Yeah, go ahead.
Additive effect going on here that it's that third ad that just nails me, or is ad number 3 the one that really has the most bang for your buck, and you might as well not do 1 and 2?
All right, so there's actually sort of 2 pieces to answer that question. One is there's nothing that prevents us from modeling ad 3's shape as a function of it being the third ad as opposed to the first and the second. There's a more difficult dynamic optimization problem which says, should I throw away money on the first 2 ads because I know that that's where my payout's going to be is on the third ad. We're not going to try to solve that problem. But if you have a best response function that tells you how effective first ads, second ads, and third ads are, then you can start asking about these dynamic strategies. You can start simulating them. So, yeah. Does that answer the question? Okay. All right. So you know, in some sense, there's this concept called multi-touch attribution, which is how much of the effect of an ad, or sorry, how much of the effect. So when someone buys. Makes a purchase, or when someone signs up for Netflix, how much credit should we give to each one of the impressions? Or how much credit should we give to a particular publisher for generating these conversions? And so the challenge is that this is usually what you get to observe over time. You get to observe something like a histogram, a continuous time histogram of when conversions happened over time. The conversion doesn't show up and say, hey, I was caused by the ad, of course, or I wasn't caused by the ad. I'm a baseline conversion. I wish it did, then I wouldn't have to do any of this work, and the problem would be solved. But the nice thing about the model is that it allows us to actually estimate these things. So we can construct what we call an incrementality share. So in this case, with the model, we're able to estimate the baseline, which we do through the experiment, versus the incremental effect, which we do by modeling the dynamics of the treatment effect. And so what we estimate here is that this conversion had a 70% probability of being caused by the ads, and a 30% probability of not being caused by the ads. You sort of get, with that type of information, also it turns out that the value of the ad is actually just the area of the curve. So it's the integral. You integrate over time the amount of the change in the probability of an expected conversion over time. And that's like a really nice characteristic, because then it turns out that in a real-time bidding scenario, this means that all we have to do is compute an inner product. And because you have to be able to respond with a bid you have to be able to compute your bid, say, on the order of 20 milliseconds or less, it's very helpful to use very simple functions. And so this allows us to just use a simple inner product to estimate this effect. So we didn't have to do any like numerical integration or minimization or MCMC or whatever exciting things you normally would like to use. All right, so it also allows us to break down the effect into the components. I think I have another plot that makes it clear. Okay, so the first ad in this case would be responsible for 39% in expectation, 31% for the second ad, 0% for the third because it hasn't happened yet, and then in this case we have 30% for the baseline. All right. So if we have another conversion, we can do the exact same decomposition. So this is a nice thing that allows us to sort of accumulate all of the effects against many conversions of a given ad impression. So in this case, we can add the first effect to the second effect, and then we would say that the expected number of conversions that this impression drove is just 39% plus 6%, or 45%. So just this sort of additive separability makes accounting very nice. When it comes time to bring your answers together, so that you have if you have all these different ways of computing it, that they actually give essentially the same answer, either same answer in expectation or the same answer numerically. So we can either integrate up all of the user's conversions where we've estimated the incrementality share, or we can integrate it up across all of the ad impressions, or we can the impressions and their conversion components, or we can just sum up all of the total effects of the impressions. So this is really nice for if you're building a SQL database and need to be able to query it really quickly, so that people who are running ad campaigns can know how effective the ads are, so they can make decisions. Yes. All right. So so this is kind of the nice plot that allows you to see that you can estimate both the shares as the conversions are observed, as well as the residual amortized component of the ad that says how much incrementality do you still expect to observe. So when you're building a system, you need to be thinking about this so that you don't have, like when someone turns on a campaign, it doesn't say, hey, there's no incrementality, and we don't expect any incrementality. What you want to be able to show them is, here's the incrementality we've observed so far, and here's the amount we still expect to observe, so that they can make a decision that says, all right, well, should I change things yet, or should I just be patient and see how the realizations turn out? And gives more stability. Yes?
How much of this relies on having really large time lags between the different ads, between sort of the start of a new ad?
Yeah, so all that really depends on how precise your estimation is. So if it turns out that there's a really strong signal to noise, they don't need to differ at all. If it turns out that your signal to noise is weak, like it really is, then you need to start thinking about how do you introduce randomization in order to dynamically estimate these effects if you're going to estimate it using instrumental variables. If you're not using instrumental variables, then it just changes the variance and you just estimate the regression. And if you have a way to change that lag, that's great. But typically we don't have the ability to change it other than just not buying the ad. Great question. All right, so let me just skip ahead to the sort of the last two ideas that I wanted to just go into, which is there was the ghost bid question. All right, so in the case of so ghost ads, normally we would just say, all right, so suppose we have this baseline. The real world, the baseline is not constant. It's dynamic. When you visit Rotten Tomatoes to look up a new show, maybe Bird Box, and you're trying to figure out whether you want to watch it, and then you see a Netflix ad, then the question is that do you go sign up for Netflix because you were on the Rotten Tomatoes page, or do you sign up for Netflix because there was a Netflix ad on the Rotten Tomatoes page? There's a simultaneity problem. And the only way we can get around that is by randomly putting that ad on that page or not. And so we're able to do that. But we don't get 100% control over whether we put that out on that page or not, unless we want to bid astronomical amounts, and even then, sometimes you still don't win. So this would be the ideal world where either ad exposure is effectively random, which it's not, random noncompliance. This is more typical of what would happen is that when we don't win versus when we do win, the baseline moves up and down on us. And so the solution to this is something we call ghost bids, which is that if we're able to randomize its presence or not, then we get to compare it. But what we end up using in an instrumental variables framework is that we're gonna randomly change whether we win or not but we don't get 100% control over it. So what we're able to estimate is the curve when we win, or we're able to estimate this curve, which is when we win 50% of the time, and then we can inflate it to know how big the treatment effect is, just like happens in the late framework. Yes?
So all of this has been in the context of trying to estimate the best response in these auctions.
Yes.
Do you know whether truthful bidding is in fact the best response in these auctions?
So now that the second price, well, first off, in dynamic second price auctions, the answer is almost always no anyway. In static, single shot second price auctions, then people like to think about that truthful bidding is the right thing to do. Now that over the last summer, pretty much everything has moved to first price, at least in terms of the open RTB ecosystem. And so as a result now, definitely you should be bid shading in some way. And that introduces a complete, a different challenge. So I'd say that there's two parts of the market. There's estimating your valuation function, your willingness to pay, and then there's a dynamic strategy problem of figuring out, given a valuation, now what should my bid be? And so for the most part, we're just trying to nail the first question, and then the game that you play with that valuation function, knowing, like in some sense, you know the payoff matrix now, you can then start to ask the questions of, now let's put all the game structure on top of it. Yeah. Yes? Oh, sorry.
Why are they moving to first price auction?
Because people don't change their bids very often, and presumably it increases revenue. Like in the short run, if you just suddenly run an A/B test for 2 weeks, you're going to see there's a huge revenue increase. In practice, it's probably not that silly. The actual real reason is that it's a hard problem, and usually if you put a first price in, you're able to, in essence, it's like it simplifies the reserve pricing problem, and there's probably a couple other reasons why that I'm ignorant of.
Yeah.
Yes, there was one other question. Yeah.
Interaction of variables.
Yes, so you can do that. So there's nothing that prevents you from including the interaction.
So to know how much the effect of the second add is actually.
Exactly. So yeah. So if we wanted to know what's the effect of the third add, we might want to say, well, that's basically like interacting an add that has been preceded by 2 adds as well. Yeah. So you can enrich the model. The question of how much you can enrich it really comes down to signal to noise, and that's where machine learning comes in, because it allows you to then do model selection, regularization, and clean up all of this. Basically we've added those IJK features, taus. There was another tau in there because of the kernels. It then allows us to sort of clean up, maybe like take 50,000 features and then prune it down to maybe the 5,000 that actually matter. Yeah. All right. So let me conclude with this concept called the Hausman causal correction. Do I have like 2 minutes, 3 minutes? Okay. All right. So who here is familiar with? Let's see. Okay. Yeah. Let's just skip that. Okay. So who here has heard of the Hausman test? Hausman, Wu, Durbin, depends on who school of thought you agree with. So in the world of econometrics, there's this concept of the Hausman the Hausman test, which basically compares a model that you believe in but is noisier than you want it to be, with a model that you might be wrong, but you really want to use it because it gives you a more precise answer. Maybe it gave you a statistically significant result. And so the Hausman test allows us to figure out in a principled way how to select between these 2 models based off of are they giving a different answer, and then is the better model, is the worst model really noisy, or is the better model sufficiently better? So there's this minus is kind of like the key result there, if you want to go read up on it. But the beauty of this is that if you look at this result right here, if you've ever done ridge regression, this looks like L2 penalization of a coefficient. So if you can figure out how to construct a feature that will have this as the coefficient, then you just have to worry about penalizing that coefficient. So it turns out that that's actually pretty easy to do. So there's a form, you can either directly penalize it in an objective function, or it turns out there's actually a simpler way, which is known as the control function approach. So who here has heard of the control function approach, or 2-stage residual inclusion? Okay. Who here has ever estimated a first stage in an instrumental variable? So you estimate this first stage, which is the probability that you show someone an ad based on your randomization and maybe some other stuff. And then there's always going to be a residual. And so you're going to estimate this residual, which is the difference between ad exposure and predicted ad exposure. And then it turns out that another way of estimating the causal model, the 2-stage least squares instrumental variable model, is to just throw that in as a feature right here. So we just toss a feature in. And it turns out that the beta, or the coefficient on that feature, is in fact exactly what we were looking for, the difference between the 2 models. So it controls for that. And it's a really nice, so this is the key observation, that turns out that's exactly what we wanted. And so if you want to do the machine learning version of this, which is instead of it being binary, do I pick one model or the other model, let's just get the model that is the convex combination of these models that maximizes some like out of sample prediction criteria. All right. So first off, does this work? Well, it's really interesting to see that in practice it actually does. So here the black line shows the predicted incremental effect, dynamically modeled in as a simulated data using 2-stage least squares, and the red line shows what that effect is if you use just the least squares model. So you can definitely see that it's estimating it incorrectly. And so while this gap looks small here, that's just for this example. In practice, those gaps can be orders of magnitude different, as they found at eBay, for example. Then the question is as you get more sample, suppose you were to use this convex combination using the Hausman penalization or Hausman causal correction, will you eventually converge to the right answer? And the answer is yes. So what you'll see is that as we increase the number of observations, we go from something that's noisy and tends to be a little bit closer to the noisier, but wrong, the less noisy but wrong least squares answer. We then can eventually converge to something that lines up perfectly with two-stage least squares. So like in practice, what this means is that sometimes you run an experiment and it was low powered. But what you learned from the experiment wasn't exactly what the treatment effect was. You learned the distribution of where the treatment effect is not. And so you learned that it can't be bigger than the values that were covered by the confidence interval. And as a result, that actually imposes a restriction on the least squares model or the ridge model that then the ridge model has to obey if you add these control function features and then tune them, hyperparameter tune them. So like this was really what we were looking for all along is how do we use existing machine learning technology where we can just throw in some magic new features that will just suddenly make our model causal. And we do that by adding randomization and then constructing them. So in the end, we're trying to sort of convexify this space. This is sort of where machine learning lives. You have a regularized model or you have a fully overfit model. Maybe there's regularized bandits where they're using regression models to estimate bandit best response type functions. And then in econometrics, we've done a lot of things where we're just asking, do we want correlational or causal modeling? And really what we want to do is probably something that's more in the middle. So we want to find something that's sort of an optimal combination that uses all of the experimental variation that we have, but then also recognizes that the most precise model is the one that's able to use all the data. So anyway, that's all I have, and so thank you so much for your time.
Thanks a lot. More questions? Okay, thanks a lot.
Thank you so much.
And we come back in 1.5 hours, I think. And lunch is not served here, so everybody is invited to search for lunch.